Good morning, boys and girls, and welcome back. Today we are going to be talking about our comparison tests. We're going to pick up two different tests, the direct comparison test and the limit comparison test. All right, so let's start with our direct comparison test. All right, here is our direct comparison test. Suppose we have two sequences, okay, A sub n and B sub n, where they're both greater than 0, but A sub n is smaller than B sub n for all of our n values. Okay, one sequence is always smaller, A is always smaller than B. Then I know, by using direct comparison, that if the B sub n series is going to converge, then A sub n has to converge as well. Then that series is going to converge. And if A sub n diverges, that series diverges, then B sub n is going to diverge. Basically what we're saying is this with the direct comparison test. If the larger of the two series is going to converge, then the smaller one would also have to converge. And I'll show this graphically here in a second. And what the second direct comparison test is saying, if the smaller series diverges, then the larger one is also going to have to diverge. Okay? So if I've got a bigger series and I know it converges, then the one that's smaller will also have to converge. Or if I have a small series and it diverges, then the one that's bigger of it is also going to have to diverge. Graphically, kind of would look like this. This is basically what we're saying. If I've got some series that is converging to a value, some value here, if there's some other smaller series that's in here below it, as it goes in, it's also going to have to converge to that same value. It's not going to be able to grow, and go to infinity, because it's always got to be smaller than the one series. Okay? So this is kind of using the squeeze theorem is how we would prove this that we had talked about. But if I've got one that, again, if the larger series converges, then the smaller one also has to converge. Or conversely now, if the smaller one is going to go and it does not converge, it goes and grows and grows and grows, then the larger one, if it's going to have to stay above it the whole time, is also going to have to go and grow and grow and grow. And so it's also going to have to diverge as well. Okay? So this is what we're saying with the direct comparison test. If the smaller one converges, if the larger one converges, then the smaller one will also have to converge. Or if the smaller one diverges, then the larger one will also have to diverge. All right? So let's use this real fast here. Okay, I want to know if this series is going to converge or diverge. And so the easiest way to, again, prove this one would be compare something that we know. And like we talked about on the P-series day, P-series are really easy to see if they converge or diverge. So this looks similar to a P-series. It looks similar to 1 over n squared. So I would want to compare it to 1 over n squared. I just need to know, I know that 1 over n squared converges because the p is greater than 1. So I just need to know that this is then going to be smaller than that. If I plug numbers into here, if I plug in 1 to n squared, I'm going to get 1 over 1. If I plug 1 into here, I get 1 over 5. That's going to be smaller, right? And the same thing would happen. For all values of n here, 1 over 3n squared plus 2 is going to be less than 1 over n squared, right? So, by direct comparison, I know that this series is also going to have to converge, okay? Both converge. So when you use direct comparison, you want to compare it to a series we already know. Okay, so generally we're going to be comparing to P series because they're really easy to use. Maybe a geometric series because those are very easy to tell. But we're going to compare it to a series that we already know something about. And for us, generally speaking, it's those types there. And then I'm going to have to show that. Two things I need to show. I need to show the comparison in their size. I got to show that it's smaller if I'm trying to show convergence or larger if I'm trying to show divergence. And then I'm going to say they, by direct comparison, then both converge or both diverge. All right? All right, so here's our next series, 1 over the square root of n minus 1. Again, I first need to find something I want to kind of compare it to. And what I think is, when I try to find stuff to compare it to, try to strip it away of all the extra stuff. Like on the last problem, we stripped away the plus 2 and the 3, and we just compared it to 1 over n squared, right? In this case here, if I strip away the extra stuff, maybe I want to compare this to 1 over the square root of n, or n to the 1/2. So again, this is a P series, and I know that this one's going to diverge. So I now just need to think about / look at, hey, square root of 1 n minus 1. Is that going to be greater than 1 over the square root of n, or n to the 1/2? And yes, it will be. If I subtract a number from this, that's going to make the bottom smaller. And if I divide by a smaller number, that actually makes the number bigger. So yes, this is smaller than that. And again, you could plug in some actual numbers if you need to kind of compare the two. And if I plug in 2, and actually I think I messed up here. This should be going from 2 to infinity. But if I plug in 2, over here I get the square root of 2, and over here I get the square root of 1. Well, sorry, I get the square root of 2 minus 1. So this would be 1 over 0.4, and this would be 1 over 1.4. So again, this is smaller, so that's going to be a bigger answer, bigger number. All right, so now I know that this is smaller, and I know that the larger one diverges. Sorry, I misspoke there. I know that the smaller one diverges because, again, of p-series. So, by direct comparison now, both series must diverge. Okay? I know the smaller one diverges, so the larger one also has to diverge. All right, let's try another one. Okay, so here's another one, slightly different now. This one looks like we're not going to compare to p-series. If we look at this, it looks like we might compare this to a geometric series. If I get rid of that plus 5, it looks like I can rewrite this as 3/4 to the end, which is geometric, with an r that's less than 1. So I know that this is going to converge. So now I just need to look at / state that this is going to be smaller than 3/4 to the n. Again, because my number on the bottom is bigger, it's actually going to be smaller, so that works out. So because that converges, I know that our original series must converge. So by direct comparison, when this series is smaller, make sure we state those things, both series are going to have to converge. Okay, last one here, trying to find out what I want to compare this to. Let's see, if I get rid of stuff, looks like I might want to compare this to 1 over the square root of n cubed, or 1 over n to the 3/2. That's a p-series with a p greater than 1, so that's got to converge. So now I just need to look at / state that because it's smaller, and I know that the p-series converges, then both of these series must converge. If it was not smaller, okay, then basically direct comparison doesn't work. If it's not smaller, if it was bigger, then it may converge, it may diverge. I don't know. If it doesn't fit these rules, I need to move on to a different test then direct comparison does not work. I have to find a different test. And then again, as always, also I forgot to mention, but, always do the nth term test for convergence first, because if that diverges, then we can move on. But all of these pass the nth term test. And so we can move on to our direct comparison test. And then I was just thinking, another thing I forgot to mention, both these tests are still for positive term series. Okay, all of our comparison tests, everything we've talked about so far is only for series with positive terms. Okay, in this case, it doesn't have to be decreasing, but the terms have to be positive. Okay, now on to the limit comparison test. If we take two series, if I take those sequences and I divide them, one divided by the other, and I take the limit as we go to infinity, if that goes to some limit where L is finite and positive, then both are going to converge or both diverge depending on the one I'm comparing it to. Okay? So I'm going to take the limit of a series that I know that happens, again, usually like a p series, and then I can take the limit of the other one and divide them, and if it equals some positive finite number, then they both converge or diverge. So I'm going to go back to this one we talked about the other day, 1 over a n plus b, and now instead of using the integral test to show that this one is going to diverge, we're going to do this through the limit comparison test. And again, I'm going to compare this to the simpler version, which would be like 1 over n if I got rid of the a and b. All right, so it doesn't matter which one goes on top. I'm just going to take the series that I'm comparing to the one that I know. I'm choosing again 1 over n. We know that 1 over n is the harmonic series, and that the harmonic series diverges. So now I'm just going to evaluate this limit. If I simplify that fraction, that complex fraction, and skip, flip, and multiply, I get the limit as n goes to infinity of n over a n plus b. And now because we're going to infinity, I could ignore, the plus b part, and this just becomes the limit as n goes to infinity of n over a to the n, which would simplify to 1 over a. And so that because this goes to a positive finite sum, now that I know then that these are going to do the same thing. So because 1 over n diverges, then this other series also diverges. Okay, our next one now, I'm going to look at the series 2 over 3 to the n minus 5. If I'm trying to find out something to compare this to, I might get rid of some of the fluff stuff. I might think about comparing this like 2 to the 3 over n, which I don't know anything about really. But this is also kind of similar to, 1 over 3 to the n, which I could rewrite as 1/3 to the nth power, which is geometric. So I'm going to compare this to that geometric series, the 1 over 3 to the n, or 1/3 to the n power. I know that this is geometric, r less than 1, so I know that this is going to converge. I think part of the difficulty with this comparison test is, again, finding that one series that you want to compare this to. Again, keep in mind, you generally are trying to do like p-series or geometric. Okay. Once I have it, though, I'm going to set up my limit, and I'm going to simplify my limit. And as I simplify this limit, I get 2 times 3 to the n over 3 to the n minus 5. And then because we're going to infinity, I could get rid of that minus 5 part. And again, poor notation, but I'm just showing you what I'm thinking in my head here, analyzing analytically. And I would get 2 times 3 to the n over 3 to the n. And then the 3 to the n's would cancel out, and so this would basically be 2. So because, again, the limit of this is a finite positive number, I know that these are going to do the same thing. So because 1/3 to the n converges, I know that they both are going to converge. When using the limit comparison test, I don't care about if one's bigger or one's smaller, like the direct comparison test. There I had to worry about the size of the things. In this case, I just worry about what the series that I'm comparing to does. Does it converge or diverge? And I can compare the two. One does not have to be bigger or smaller than the other one. All right, so here we go. Here's another one. Got to figure out what to compare it to, so I might think about this. I would start out thinking, hey, let me compare it to 3 over the square root of n squared, which is like 3 over n, which is pretty close to 1 over n, because I know what 1 over n does. So I'm going to compare this to 1 over n, or the harmonic series. I have to set up my limit, and now that I do, I can simplify it. All right, so as I go to infinity, I get, thinking about 3n over the square root of n squared, which is n, which is then going to go to 3. So this, again, positive finite number, so they're going to do the same thing. So because 1 over n diverges, this also diverges. Okay? If it did not, again, if it failed this test, if it was something other than that, again, that just means that this test didn't work, and I now need to apply a different test. Okay? So sometimes this test won't work. It doesn't mean that it's going to diverge, if the test doesn't work. It just means that this test failed. Okay? This test, again, just shows convergence or divergence based on the series that I'm comparing it to, if I know what happens with that one. Okay, here's our next one. So again, if I were doing this, I'm going to ignore the extra stuff and think about maybe just like 5n over n squared, or again, that's like 5 over n, or I'm going to compare this to 1 over n, compared to my harmonic series. You'll find that that's a common thing that we will compare things to often. Set up my limit, and now I can go ahead and simplify. And we get 5n squared minus 3n over n squared minus 2n. Again, we're going to infinity, so ignore the other stuff, and we're just looking at 5n squared over n squared, which is going to go to 5. So again, because the harmonic series diverges, this series also will diverge. You'll see that this is a pretty useful test. We kind of like this one. It's fairly easy to work out. So, good one to kind of keep in the back of your mind. Okay, and our last one here, and again, I think these are the most difficult when they actually just give me the series written out, and so I need to come up with that explicit formula so that I can use the, limit comparison test with it, or use the direct comparison test with it. So in this case here, if we're looking, I think if I were to rewrite this, it would look something kind of like this. Hopefully you recognize a pattern with our numbers. I say that the top is always 1, so we'd start there, and these all start with 200, so 200. And then I'm adding perfect cubes, so 200 plus n cubed. That would be my explicit formula, and that seems to work out perfectly for us. And so now I can look at something to compare this to. Again, I might compare this to 1 over n cubed, which is a p-series, which I know that is going to converge. So in this case, again, I set up my limit. I flipped and multiplied. I got 1. So again, I know that because I got a positive finite number, they're going to do the same thing, so they both are going to converge. Or again, in this case, you could have used the direct comparison test. Because this is going to be smaller than this, right? Then I know because that one converges, that can converge. You can use direct comparison or limit comparison. Again, that starts to become part of the hard part is, which test do I use? And I'd say use the ones you feel most comfortable with first. All right? That's good for today, boys and girls. See you later. See me if you got questions.